So, good morning, everyone. Welcome to the session, Robots as Design Interfaces. We want to look a bit beyond using robots for mass fabrication, but towards mass customization. So, my name is Johannes Braumann. I'm one of the co-founders of the Association for Robots in Architecture. I am university professor at UfG Linz, and I'm also the main developer of Cougar PLC, the software you're going to be seeing today. As a jet-lagged European, for me this is now the best time to hold a lecture, but I really appreciate you coming here quite early, so thank you very much. Ideally, I think we would do questions at the end. However, if you have a really burning question, just raise your hand or signify, and then we can do this also in between, okay? So I want to kind of showcase the developments that have been happening in the area of robotics within the creative industries in the past years, and then also show you how these are now also transitioning from the creative industry to other industries that are also utilizing these methods. I also want to point you out towards the handouts that you can find in the download section. So the handout on the one hand contains a link to the software. So if you're using Autodesk Dynamo, you can actually immediately download the software and try it out for yourself. So we actually would really like you to try it out and to provide us with feedback. We tested it on our PCs, but maybe we find out it only works on ours and on none others. So this is a realistic risk. We're really looking forward to feedback. The PDF also contains step-by-step instructions just for really the essentials of getting started using this kind of visual programming with robots. So today we'll be having more of an overview, but this should help you get started. We're also happy to provide support, so all the information is actually then in the PDF. Finally, in my presentation, we're not just going to show projects that we did ourselves by Robots in Architecture or from our universities, but also from some of our partners that are using our software. So actually in the handout you have links to all our partners. So if you believe that some project is interesting, if you want to have something, robot 3D printing cocktails, if you want to look into high-end timber fabrication, then of course you're very welcome to contact them. And we're also welcome to put you in touch, because sometimes it's easier if you get the contact directly than just going to office@mercktimber.com or whatever. So please just get in touch if you could then any questions. So yeah, but before we get ahead of ourselves, I think the main question is now at the beginning what kind of robots we're actually talking about, because robots can basically be anything. So just today in the morning they posted some new videos from Boston Dynamics with a four-legged robot running around and acting more or less like a dog. And yeah, for us, we're really thinking about industrial robots or robotic arms. You probably know them from the automotive industry, and maybe you visited one of the automotive construction plants. And in the automotive industry, the reason why they really like to use robotic arms is that it's just much more affordable to take a universal machine like a robot, equip it with the tool you need for that particular operation, then you program it, and then the robot is going to perform that operation over its entire life cycle, which usually is like, I don't know, 5 to 7 years of 24/7 operation. This works really well for them. But the thing is really that this is mass fabrication. So the robots are programmed once with a comparably high effort, and then they keep on running and running and running. For our purposes, we're not so much looking towards mass fabrication, we're really looking towards mass customization. So maybe you've seen the Forge keynote yesterday, where they also referred to this idea that you want to personalize, customize, you need to adapt products to certain conditions. This might be high-end architecture fabrication, where you want to cover a free-form surface with panels in a very efficient way. This could be also providing customized product that fit the requirements of the person who ordered it. We got to robots quite many years ago. So we, in that case, is my colleague Sigrid Jogjan, who's now professor at RWTH Aachen in Germany. And in about 2007, I would say, Sigrid got the funding to buy a CNC machine. So this was a research project with the geometry department, and the idea was to look into multi-axis fabrication for architecture. But they had a budget of around 100,000 euros, and that was really barely enough to get like the cheapest 5-axis milling machine at that point in time. I think it has changed a little bit, but at that time this was just the price level that we were at. And that machine wasn't really trust-inspiring, so it didn't, even during the demonstration, it broke down. So this was, of course, a bad start. So we figured we need something reliable, but at the same time, we want to have something innovative. So just getting a 3-axis milling machine and saving 50,000 euros wasn't really an option. So at that time, KUKA approached us and told us that they have a product that would allow us to take G-code meant for 5-axis machines and then use it on an industrial robot. That was called KUKA CAMROB. Now it's called KUKA CNC. And that was actually for us the reason to say, well, we're going to take a risk. We're not getting a proven CNC machine. We want to look at robotics. Of course, it also helped that with the idea of research, of course, we wanted to go somewhere where there isn't that much existing projects going on here. So we got the robot, we bought the software, so all of that somehow fit into the 100,000 euros. And that is the kind of workflow that was provided to us by KUKA and the CAM company. So basically, if we wanted to mill with the robot, we had to first make a geometric design in a software like Inventor, Rhino, or maybe now Fusion, but that didn't exist then. Then you would have to export it in a generic format like IGES or STEP or something like also DXF if you really want to. And then you put it into your CAM software, into computer-aided manufacturing. So this would be, for example, today Power Mill, if you want to have an Autodesk product for it. From there on, we again had to export our 5-axis G-code to the robot simulation environment that would show us how the robot would move in order to fabricate it. And only then we would be able to send the file to the robot. So that's a workflow that actually works pretty well for industry if you want to do individual prototypes. So we work with partners who do large-scale stone sculptures, and this is a workflow that's perfectly fine. However, for us, all of that was quite complicated because when we're looking into the milling software and then we see that there would be tool reachability problems or some problem with the geometry that it didn't import correctly, we had to go back to the geometric design. Or even worse, if we realize in the robot simulation that the robot cannot reach that point, we might have to go several steps back in order to be able to solve that issue. So that's not so much of a problem if you're a very experienced CAM or robot operator. So at some point you get a feeling how all of that works, and you can go through that workflow quite well. But for us, the problem was we were looking at education, and we were looking at people who didn't have any previous CAM experience. So actually, in our teaching, we spent the entire semester teaching our students software that they most likely would never, ever use again. And the robot was really like the part at the very end of it. So we didn't spend the semester working with the robot. We actually worked three quarters or even more of our time only on software. And then at the very end, we had a few days of fabrication. And that was not really what we were looking for. And at the same time, at this stage, there were also then developments that were looking more into programmed geometry. So not so much this kind of traditional way of drawing something for fabrication or 3D scanning something that you fabricate, but that you actually start looking into fabrication and design as kind of one process. So that was one of our first some experiments that we presented at the university. So you see that basically in this case, we don't only design geometry, we actually design tool paths. So whenever the tool path changes, the geometry changes along with it. So basically it has got both of these aspects in the same kind of project. But in order to fabricate it, we really had to kind of dumb down the parametric geometry that we have. So we had to, again, save it as an IGES or whatever, bring it to the milling software, where we actually had all the information already that we needed for fabrication. And so this was, for us, kind of a problem, of course. And the other thing is, it's not very difficult to really generate code for the robot. So that you just write your machine code for the robot, this is something that you can achieve quite quickly. But the tricky aspect is really how to get the simulation right. If you don't get the simulation right, that's a project where we had 8 liters of glue for a student project, and they programmed all the position in the bucket. They didn't simulate how the robot would then, from the last position, go back to its home position. So, yeah, that happened. Anyway, yeah, let's not look at it again. The other way, of course, to approach this is that we just say, well, we want to script that. Several scripting languages, we could do this in Python or whatever, so we script our constraints, then we put it in the simulator, then we debug it, we change it again. But this was also for us not really where we wanted to go. So for us, we wanted to have something like on the right side, that we have one unified environment that contains the geometry, but also contains the fabrication. With the idea being that whenever you do something to the design, you're going to see how it affects the simulation and how it affects the robot, basically in real time. So to skip a few years ahead, this is how that is looking now in Autodesk Revit and Autodesk Dynamo. So this is just like the very simplest example. So you draw a curve, then you basically divide it into different segments, and then only at the very end you plug in the components for the robot, and you can immediately see how the robot is going to react when you fabricate it. So here you already see that there's a problem. So the robot has certain limits for its access. It's going to collide with each other, so you can't do that. But now you can just change the curve, and the fabrication updates along with it in real time. So the idea really being that rather than having to know all of this by experience or by very lengthy trial and error, you have this immediate feedback. So you need to think of it a little bit like digital photography. You take a photo, you see what the result is, you can react on it. So you can work with this in a more intuitive but less systematic way, which is good. But of course, if you have this knowledge, you can also very quickly implement that. And the nice part about the visual programming, of course, is that we don't need to expose people to all the logic that's happening in there. So basically, we have a component that has a certain set of inputs and a certain set of outputs, and you don't necessarily have to know what's happening inside. For you, it's just important to understand, if we put that in, what do we expect to get out on the other side. So now to go back quite a few years again, we started to do workshops. And because we figured this would be a method and an approach that would be relevant to many people. And we're quite astonished at the very beginning. So this was our very first workshop, actually. We got many people from industry, also universities, who were also looking into these kind of problems and were looking to solve them. But we also figured out at the same time that if we're just 2 people doing workshops, driving around, this is not really sufficient to have an impact on the creative industry or even at industry. So for us, it was kind of the impact to say we need a platform. We need to have a network of users of these robotic arms, of industrial robots, of these processes, so that we can exchange knowledge and also distribute it much more efficiently than just the 2 of us. So in 2011, we founded the Association for Robots and Architecture, at that time as a spin-off from TU Vienna. On the one hand, as a network of robot users, but on the other hand, also as a research institution. So that has grown quite a lot since then. So this is a map of the members. So we now have about 100 university members worldwide. So you see kind of the hotspot where there currently is the most development, and also 50 commercial members, people who use our software for commercial purposes. And this really also spans a huge range of applications. So this is not just in milling or not just in 3D printing, but also on all different kind of levels. So on the one hand, we have very large companies who have machines that can process 50 by 4 meter elements of wood, like in this example, Merck Timber, who use that kind of approach. Whoops. Yeah. Anyway, so this is how they, for example, work. So this is really high-end fabrication for architectural purposes. They did projects like the Elephant Hall in Zurich, if you know that, and also some very interesting projects in Barcelona, and now also even more in Switzerland. And on the other hand of the spectrum, you don't have this kind of multi-100,000 euro installation, but you really have people who go on eBay, search for KUKA robots, and basically buy the cheapest one, and then are very happy when they finally get the robot to do what it's supposed to be doing. So this is a group that calls themselves Silly Swords in the Mud, and they build boats in Great Britain. Otherwise, the range of partners really spans many industries. So we have companies like Boeing and Adidas. We have companies like Merck. We have quite a few universities, as I mentioned. And I think a really key for this kind of efficient exchange and advancement innovation is really that we have so many different areas where people are working in, and this kind of cross-disciplinarity is really a turnkey for successful development. As a network, of course, it's also important that we promote this via the internet. And so these are just some of the facts. So depending on which industry you're in, this might be large or this might be very small numbers. But if you see this in context, if you think about how many people are using robots in this kind of purposes, we on the other hand have 15,000 downloads each year. And the Springer Link, this is like a scientific publication house, and having 140,000 times people access these kind of research papers shows that there's definitely an impact. But of course, having it online is just one part of that. A big part is also about meeting offline, basically in the real world, discussing the kind of problems and having an outlook. So every 2 years, we organize conferences on robotic fabrication in architecture, art, and design. We started out in Vienna 2012. Then we were at the University of Michigan in 2014, at the University of Sydney in 2016, and in 2018 we're going to be at ETH Zurich in Switzerland. And one part of that is conference panels. So basically what we are having now, lectures. But another big part of the robot conferences is that we have 3 days of very intensive workshops. So people not only talk about these developments, but can really experience it hands-on. Because as you definitely know, if you make a video, it's very easy to cheat, but if you do this hands-on, you really see the issues and you can learn much more from it. So this was a project from the University of Michigan at their conference 2014. This was from Bot and Dolly, so maybe you know them. They were now have been bought by Google, so they experimented with this kind of skill transfer from motion capturing to the robot. Or this was ICD Stuttgart, who've developed these really impressive carbon fiber structures and also showed on-site how this actually worked with 2 robots cooperating in a smaller scale. So if this is something that's interesting to you, you still have quite some time. So this is going to be in mid-September 2018 in Zurich and Switzerland. And just to kind of explain how we're internally made up. So initially, we had the Association for Robots and Architecture. We also have our Robots and Architecture Research LLC for commercial projects. And then we have our 2 university chairs, the University for Arts and Design in Linz, where I've got my professorship, and my colleague Sigrid is professor at RWTH Aachen, where she's got a chair for individualized production, and where they are also very much involved in the area of construction robotics. So in Linz, a very big part of our work is done with the Ars Electronica Center, which is one of the largest digital media centers in the world. So we work also on projects that don't really involve physical fabrication, but can be more installation. But at the same time, we work with craftsmen and SMEs to really bring or make robotic processes available for them. At Sigrid's chair in Aachen, the idea is to look into large-scale architectural production, the digitization of the construction site, and really bringing robots on-site. So we closely work together, but we try to kind of arrange projects so that we can best support them. So you've already seen quite a few projects that have been done with robots. So maybe the question is, what can we actually do with robots? And the answer is a bit flat, but basically you can do nearly everything. If you feel like you want to feed your baby, which I don't recommend, but if you want to do that, it's definitely possible. This was for a digital media project with a German broadcasting company called Homo Digitalis. But, so we took very good care of the baby and the robot, so everyone left happily. And, but basically, whatever you do, it's not enough that you can just program it. You really need to know about the material processes as well. So if you want to use a robot to structure stone like this, then this is not just programming. You really need to know how to do this by hand. You need to understand how all of that is working. There is, of course, some software that supports you. We already saw the milling software. And for example, here we have Autodesk Fusion. And we can also deal with this kind of information in our software environment, turn this into robot code, simulate it. But sometimes you have special purposes and special requirements that you really need to do something that is beyond the scope of industrial software that, of course, is made to cover the most common requirements. So this can be basically a big range of things. Here we had a project that was done by two artists, Neugebauer and Köldorfer, for Red Bull. So this was a monumental 17 by 23 meter aluminum sculpture for the Formula One racing track. And even though you might not really believe it with Red Bull, the main constraint that they had here was actually the price. So they drew all the forms in 3D, then they sent it off to manufacturers, and then they got quotes back that were extremely high. Probably you know that if the manufacturers are not 100% confident in your capabilities, they would just add 50% on top of that. So this probably also happened there. So for them, the idea was, well, let's just do it ourselves. They knew that we were working with Robots AT of Vienna, so they got their own robotic arm, bought it used in Germany for 20,000 euros, put it on the truck, set it up in their lab. What they then actually realized is that the robot itself is, of course, not enough to fabricate. They had the idea, you take a 3D model, you put it onto the robot, you click play, and then it would build the piece. If you've worked with CAM software, you know that this is not the case. And especially the CAM software used to drive the robot would cost more than the robot itself. So basically, we worked with them to create this kind of customized interface that would allow them to perform the operations that are needed for them. So not like a universal solution that you get out of CAM software, but something that is very specific for their purposes and allowed them to do that. And the special part about this is that we, of course, didn't have an interest to spend several months away from our own work, away from whatever, to fabricate a huge monumental bull for Red Bull. So the idea was really to have this kind of knowledge transfer. So for just 4 days, we worked with the guy in yellow, who was the son of the artist, who was basically shanghaied to work on his father's project. And over 4 days, we taught him how to use the robot, how to use the software. And then they were really able to fabricate it. And what's special about that is that the guy didn't have any previous knowledge about CAD or CAM. So he hadn't ever used any kind of CAD software before. He had studied tourism. But still, the kind of 4 days were enough for him to kind of understand the essential parts that would allow them to really fabricate this by themselves, then cast this kind of positive foam parts into aluminum, and then set them up on site. Here with Züblin, that's of course the other side of the spectrum. So this is very high-end architectural fabrication. This is for a train station in Germany. So these are these kind of free-form columns. So you see there are several of them. They all look differently. And each of the formwork for these kind of structures up here, the columns, again consists of this kind of individual elements. So if you do this traditionally, you end up with having, like, I didn't count them, 12 or whatever elements per column. Then you have so and so many columns, and you need to process each of them automatically. Not automatically, manually. But of course, the thing is, all of these elements are individual, so they have a different angle here, they have a different curvature, but the general topology is the same. So in that case, the approach of Züblin was to say, well, if they use Grasshopper, they don't have to process everything individually, but they can extract that information from the parametric model, do the fabrication, and then send this to the robot much more automatically than before. Because as I said, they all basically work the same. You only need to be able to adjust the angles. At the same time, the motivation for them was also that they didn't want to use kind of standard CAM software. So their idea was that if they use CAM software that all the competitors are using, they don't have a competitive edge. So instead, what they wanted to do is that they wanted to be able to take their own process and material knowledge, put it into the software, and then benefit from it. And they're doing this through visual programming so that they can very easily adjust and modify that. So this is just a very simplified example how that could work. So you have your free form out of Revit, it's panelized into different panels, and then you can just automatically generate your files for each and every part. So you see they all look similar. In this case, they all have 4 corners, but at the same time, everything is individual. Of course, this is kind of slow scale. You could just do this automatically and get a bunch of hundreds of files, but this way you can actually see what is going on. And you especially need this if you want to adjust to more individual parts. So this is a project by the Architecture Association at Hook Park in London. It's a research pavilion that they developed with actually like found wood. So they needed processes that are able to very quickly adapt to the local conditions, which in that case is, for example, the size and diameter of the piece of wood. And then, of course, do this very efficiently for many pieces, so that they were then able to assemble this to one continuous structure made out of individual found wood elements. And then sometimes you have projects that you do by hand. So, for example, hot wire cutting. So many of you have probably done this before. So that's a company in Germany, Artis Engineering. They work in prototyping, and they need to fabricate things very efficiently because they don't do this in high numbers. They do this for a customer. Maybe there's only one piece. And if you do this by milling, you would have to cut away everything that's basically here. So this takes very long and produces waste and all the other kind of problems. If you do this by hot wire cutting, you see in 5 minutes you cut through, and with this geometry you can very quickly and efficiently fabricate it. Now the thing is, there is no really a software for hot wire cutting. So again, for them the idea was they actually built their own hot wire cutter just out of aluminum profiles and a wire, and then created their own software tools, and then bringing that together, they had a completely new solution for that. And of course, then in visual programming, again, just a very simplified example, if you can also look at all kind of elements, so you can check, does the reachability work, does it not work, does it cause problems? And some kind of applications you can, of course, solve by brute force. So if you want to bend metal with a robot, in this case, to be entirely honest, it was just enough to have enough payload for the robot and bend it with as much force as it had. So this was for a company called Tulco. They do mass customized furniture systems. So they have their own iPad app where you can adjust your furniture to your living room, and they wanted to look into how they could work with metal. But then, for example, if you want to do knitting with robots, so this is a student project from Poland, then of course it's not enough that you just know how to program it, but you actually need to understand the process. So probably you need to do this a few times by hand in order to then really get the result that you require. And I mean, again, this is something that, just like hot wire cutting, we've been doing by hand. But of course, we can also do then new things. So maybe we don't knit with some kind of wire, but maybe we use wire and resin to create structural panels. So this was by the UfG in Barcelona at a visiting school in Moscow. And if you work with new materials, with new processes, it's not enough just to develop the hardware. As you see, you also need to think about how do you develop the processes. So for example, this is a new 3D printing process developed by an Italian research lab. And they had the idea of 3D printing like a silkworm. So they didn't want to melt plastic, but they actually extrude fiber that has been put through resin, and then the blue light that you're seeing is then UV light that's used to harden it. And if you want to do something like that, it's not enough just to take your standard 3D printing software and use the G-code from that one, but you see that it actually has to tilt the tool. So you need to define a strategy how you can extrude that in an efficient manner to do this with a new process. And of course, you also get new challenges if you go up in scale. So it's one thing to print in small scale, but printing in large scale has its own challenges. So that's one of our partners, Branch Technology. They're based in Chattanooga in Tennessee, and they developed a large-scale 3D printing process. But this is not university research. as you've seen before, but this is then really industrial research. So they're a company, they're, as far as I know, venture capital funded, and are really now bringing this out in large scale. And having this kind of custom interface allowed them to create their own logic that their competitors don't have, and then to build up on that, to improve on it. And now they're already working on very large scale, like these kind of structures, and are also, for example, involved in research. So this is done with Foster & Partners, a big British architecture office, where they won the NASA Mars Habitat Prize. So they developed these kind of strategies, how we could 3D print in the future to create structures on Mars. And sometimes robotics is not just about fabrication, it's also a tool for, I would say, just entertainment. So for example, this is a project that was, is a spin-off out of my lab. It's called Print a Drink. And it was developed by Benjamin Kreimer with the idea of printing liquid within liquid. So this is not some kind of structural element. This is not 3D printing for construction. This is really for marketing. So he offers this to companies that he puts at events, his own logo into the cocktails, and then people can drink it. And this actually resulted out of a university course. So we had the concept of thinking about machinic food design. Do something involving food, but don't duplicate what you do by hand. Think a bit further what you can do. And he developed the liquid printing, and then really was able to push that into a startup. So he's now very successful, has its own robots, and offering this to companies both in the States, but also, of course, very much in Europe. And here the nice thing really was that the robot was something that came at the very end. So the semester was really spent on material research. So this is the kind of proprietary knowledge that you have in here. The robot at the end was a tool that was very easily added, and he developed his own like deposition tool, which is basically just some medical equipment put into a 3D printed environment. So basically, the robot allowed him to have this kind of proof of concept that it works, to show people, show investors that this is something that's viable. And now he's actually building his own machine to do that, but of course, like this. Because in a bar, you probably don't want to have a robot standing somewhere. I mean, actually, yesterday in Las Vegas, we were at the Tipsy Robot Bar, where they have robot barkeepers. So this doesn't apply to Las Vegas. But usually, you might not want to have a robot in the bar, so now he's building his own machines. And yeah, sometimes it's not just about entertainment or fabrication, but it's really just about entertainment. So for example, this is a company in Australia called Seed, and they actually use our software to create movement for a RoboCoaster. So that's a KUKA robot that's specially certified that you're legally allowed to mount people in front of it. And they created their own virtual reality experience and then used our software to create a robot movement that then works parallel along with it. And yeah, it seems fun. So this was kind of a wild ride through many different projects. So in the last 5 minutes, I want to give you kind of an overview, kind of an outlook on which direction the research is going, and also kind of the challenges that we're facing. So we want to look into real-time interfaces, man-machine collaboration, and then also cloud robotics. So real-time interfaces is something that might seem very primitive to you, because you're used to taking a printer, plugging it into your laptop with your USB cable, and then you can immediately stream commands or print jobs to it, and it just works. With robots, we have the challenge that they're not really made for that. So we can either control them in hard real time, which is an issue to do, for example, out of Windows. So it's a bit technical topic, so we skip that a little bit. But the other way is, of course, that we need other ways how to do that in a safe and reliable way to get commands from our very flexible visual programming system to the robot. So there's only been some developments recently, and KUKA developed a system called MX Automation. And MX Automation is actually made not for visual programming or not for this kind of normal programming at all. They actually developed it to have CNC machines, CNC controllers, so-called PLCs, be able to control a robot. So the idea being that an operator who knows how to program this kind of PLC, this kind of industrial computer, then doesn't have to learn a new programming language, but they can immediately program the robot along with it. And we kind of adjusted the system so that we can not only do this out of these very specific PLCs, but that we can integrate this into our Windows-based, .NET-based robot programming library. So in that case, we only have this kind of code on our side, dealing with the geometry, dealing with the toolpath, and then actually on the robot side, all of that part is provided by KUKA, which is for us very good, because then these are technologies that are very easy to hand off to partners. Whenever you do something that's very specific, that needs very specific hardware, it makes it hard to make it available to partners around the world. And you have to know that we're working with universities who, of course, sometimes might be a bit reckless. So they see some code on the internet, and they just start it. So that's a bit of a challenge for us. So this is for us a safe way that we can communicate with the robot. But of course, you need to think about how you can do this kind of communication. And in that case, we always have a command buffer. So this is basically some storage at the end that saves the commands that are sent to the robot and then execute it. So we don't have to always keep on sending commands as long as the buffer is full. But then we can create these kind of processes that then always change between evaluating and then doing something. So the robot would 3D scan, our visual programming environment would generate the toolpaths, then it would do that, then it would go back again. Or it could automatically process many, many pieces based on real-time data. So we first presented this at actually Autodesk University, but in Germany. Just some very simple examples here. And then again, we did a hands-on demo at the AAC Hackathon, also hosted by Autodesk in Munich, to kind of present purpose utilizations, how you can use then real-time control of robots in your own design systems. Yeah, maybe that was a bit technical, so let's go to a bit more fun process, man-machine collaboration. I'm not really thinking about man-machine collaboration in this very idea that you always have robot and machine working next to each other. So in that case, I'm kind of more thinking about what can the robot do and what can you do by hand. So this is actually the output of a project we did with the University for Applied Arts in Vienna. It was called Robotic Woodcraft. We're looking into more arts-based application of robots. And this was one of the processes that was developed by one of our research assistants. And he had the idea that he can very quickly manufacture these kind of ruled surfaces with a robot, because for a robot doing this is very easy. You just make these kind of holes. It's done in 5 minutes. If you do this by hand, it always takes ages. But something that you cannot really do by hand is what you cannot do with the robot properly is the assembly. Because the problem is that you always basically program the robot at 0 tolerance. So the robot is very accurate, the robot is very precise. You tell the robot to go somewhere, and it's going to go somewhere. With wood, we have the problem, and with actually most materials, that there are always some tolerances. So this kind of wooden rods, they're always bent in some degree. If the humidity changes in the air, also our wooden rods change. So that's a problem for us. And we always, again, had to do this by hand. So for our research, together with KUKA, we wanted to look into ways how we can get a robot to deal with tolerances. This also looks in this future idea of having robots on construction sites, where you also have this kind of problem that you might have a very accurate 3D model, but it doesn't really mean that the 3D model coincides with the actual physical environment. So this was something we did for the Hanover Fair in Germany, which is one of the largest industrial fairs in the world, for KUKA, and we used a very special robot for that. So you see that robot up here looks a bit different. It's a KUKA LBR EVA, with EVA standing for Intelligent Industrial Work Assistant. Basically, they built the robot to be safe to use next to people. If you have a normal robot and you tell it to go from here to here and you're standing in between, you will probably get hurt if you're not quick enough. So that robot doesn't have any sensors. It's just going to go from here to here, and everything else you need to take care of yourself. That robot has got force sensors in every motor. So if it feels resistance, depending on how you program it, it's going to stop. But we wanted to use this kind of sensitivity a bit different. So not only for safety, but also for assembly. So for this kind of trade fair installation, we basically first captured some initial data, because we didn't want to have everything the same every time, because then it would be kind of faking it. So in this case, actually, people took the robot in front, and then they captured this kind of curve, and that curve was then the information that we used to inform the fabrication process. The next step was then for the robot to take the rods out of a magazine, so they are not placed very accurately, they're somehow thrown in, so this is not super accurate placement. And then the first thing it has to do, it has to figure out how long it is, because they're not very accurate, as I talked about. So actually, whoops, that was cut away here. Actually, what it did to measure that wasn't using some kind of optical sensors, but it just took the rod, went down until it collided, then it knew how long it is on that side, turned around, went down again, then it knew how long it is on the other side, then it had the total length, so then it could cut away the part that wasn't needed, and then it would assemble it on site. And the assembly, again, works a bit similar like we do it by hand, because we looked into how you assemble by hand, and actually just by looking at it isn't really enough information to put something like that into a hole. So we usually get the rough information by looking at it, and then we assemble by feeling. And we did the same here, but we didn't have a camera system. So instead we had our ideal 3D model that told us this is where it's supposed to be, and then the robot, with the sensitivity, adapted to it in real time. So it just meant this kind of zigzag movement, and once it slipped in, it knew now it's at the right position, and it can release. So this is how all of that then looks in one entire process. So you can teach it the curve, then it measures on the back how long it is, and then it assembles it. So this is now not some kind of architectural structure or pavilion or whatever. This is really a fabrication prototype showing how this kind of processes can be used. For example, in environments where you don't have optical sensors. So 3D scanners are great, but once it gets dusty, once there is big humidity, you run into issues, and then having this kind of processes is valuable. So you can program that robot out of the visual programming environment. You actually also have the robot on a mobile platform that's available in Aachen, so you can have this very small robot cover very large environments. So this is going to be a very big part of research in the future. To close off, I want to look a little bit into the cloud. So what we've now seen were processes where you use visual programming, where we use, for example, Autodesk Dynamo to get processes from our CAD to the robot. And this really lowered the kind of entry level considerably. So you didn't have to be a robot expert to use it. You could very intuitively work with it. But again, this is assuming that you know about CAD, that you somehow feel comfortable looking into visual programming, even though it's only visual programming. But of course, this is not something how you could reach the end customer. So this was for us the motivation to actually bring our entire library into the cloud and then work with the Autodesk Forge environment to visualize it in 3D in the browser so we can actually make processes available to the end user. So as a prototype, we actually took Print-to-Shrink again because it's a project that doesn't have very high geometric requirements and is a good demonstrator to show these kind of processes. So basically what we can do now is that we have our robot library running in the browser, actually in the background. So you have this idea that you open up, you add an event, you can basically create your own structures, you can enter text, you can place your points if you want to draw something like this by hand. So you create your own three-dimensional structure, and then with the robot, you can immediately simulate, see how it works, and use that as a basically design input as well. So I mean, as you see here, it's basically, here we don't actually need this kind of robot simulation, to be entirely honest, because this is a process that always works. But a big part here is really about having the robot as an aesthetic fabrication device. So having this kind of robotic cocktails, it's cool because the robot is doing it. So this is why we also implement it here. But now that we've did it once, it will be possible to do this, of course, for very different applications. And as I said, we have exactly the same kind of logic that we're running in Dynamo. We have then also running in the cloud. We can access it. We can implement it into our own applications. A challenge, of course, when you go from the cloud to the physical robot is that we have our infinitely scaling cloud, so we can have hundreds of people using Forge, using Azure at the very same time, but at the end, we only have one machine. And that's a bit of a problem, because then we get, like at an event, hundreds of orders, and actually nobody knows who did which set of points. And so in that case, we solved it in a way that you design something, you save it in the cloud, you get your QR code, and then with the QR code, you can then go to the robot, scan it, just like you do at the airport, and then in this case, you get your customized cocktail delivered right on site. So I think this is kind of a good outlook and where this is going, because robotic technology and cloud technology then really opens up new ways for young and innovative people, for startups, to create entirely new processes that weren't done before. So if you think about the Amazon cloud, for example, they didn't do something completely different. So they used industrially available tools, but for the first time, they allowed startups to scale to do entirely new things that weren't done before. And robots have been around for a while, but now we really have the tools to utilize them. Even as a small company, we can go ahead, buy 10 used robots for probably like 100,000 euros, and then we have our own factory. And we can offer customization, we can offer products that maybe large companies cannot offer. So we believe there's a really big potential in this kind of area for new users. At the same time, we also see that more existing large companies are really looking at this kind of processes. So in our community, there are now people who studied architecture and design working for companies like Nike and Adidas, but not in design, but really in robotic fabrication. They're being hired by Boeing, they're being hired by Google for robotics research. Because the idea is really that it's not enough anymore to know about programming. If you do something complex, and you have a programmer that doesn't know about the process, whoever is in charge has to be extremely careful how to explain something, and most likely you're not going to get what you ordered. If you have people who know about both the process and the material and the programming, this is how you can then really achieve innovation. So yeah, it's a very young, very enthusiastic community. So I hope I kind of made robots sound interesting to some of you. And ideally, maybe you can join us next year in Zurich, participate in a workshop, get some hands-on experience. And in the meantime, I'll be very happy to answer any questions you might have, either now or then just send me an email whenever you feel comfortable. Thank you very much. Do you have any questions? I get this quite often, that somehow...
To be honest, can you go back to that previous picture that you just had?
Whoops, no, that one.
Yeah, why does that guy in the white shirt look like he doesn't want to be in that picture?
Let's see. Oh, yeah, he looks very serious. So he's going to be photoshopped out for the next presentation. No worries. So we kind of this liquify tool in Photoshop where you can... Awesome.
Where do we download the presentation?
Yeah, I need to repeat the question. So I was asked where to download software. Basically, I think it's on the homepage of the lecture. So I uploaded a PDF with the class material. So I think if you're logged in into the Autodesk conference system, you're just going to download. And basically, this is the PDF that you got. And here we have all the partners. So if you want to have your cocktail, you go here. Or if you want to be thrown around by a robot, you go here. And this is where we uploaded the course material. So if you go there, you're going to get an installer for the software. You're going to get some examples. And you're also going to get this kind of very quick walkthrough, just with the initial steps to get the first version going. Yes? Yeah, so the question was basically how to get a robot, or if I can afford a robot. The nice thing really is that there is a used market for robots, because the difference, I would say for CNC machines, there is no proper used market. Maybe sometimes you get a machine from some company that went bankrupt, but basically you use a CNC machine until it breaks down, and then you don't want to use it anymore. Robots for companies are really cheap enough that it makes sense for them to replace them before they break down. So this is the kind of idea that you can get a robot quite cheap. So as I said, you go on eBay. I wouldn't buy the like 4,000 euro version, but I know for 10,000 euro, you can really get a machine that is still very much usable. And you also get a very large machine. So you saw a project with small robots and large robots, and actually the large ones are much cheaper because, I mean, not if you buy them new, but in a used price, they're cheaper because there are so many of them on the market. So that actually makes them very accessible. It's just really important to consider that robots, to be entirely honest, are always like the second best choice. If you want to do milling and if you want to be highly accurate, it makes sense, if you can afford it, to buy a machine that's very specific for that job. So the appeal of robots for me is really that you can do many different things with a robot. And it's kind of interesting actually how this started more as something from the creative industry, saying we have one robot and the robot can stack things, mill things, 3D print things, and this is interesting to us. But now with this kind of idea of Industry 4.0, with flexible cybernetic systems, whatever, this is now also getting more to industry, where they say they want to have one robot that's able to do multiple jobs that they can apply once for that part, then for that part. So it's kind of interesting to see how this then comes together. But again, if you want to do really high-end milling, then, and you got the money, then of course it makes sense to go for a 5-axis milling machine. But yeah, for us also something that's been quite important, that it depends of course on the setting, is actually transport. So that might sound a bit silly, but if you want to have a machine build something very big with like a porter machine, your machine is going to be larger than your workspace, of course. And with the robot, you actually have a rather compact machine. So you don't have to disassemble it and then reassemble it in the room and also spend tons of money of that. But actually, you can just put the robot on this kind of small cart, bring it there. We had ours set up, a big one again set up like 2 years ago, and we thought that the moving company would bring like very high-end equipment to place the robot. Actually, they just had this kind of small wooden blocks, and they put in one wooden block, then they pushed it up, put in another, then they pulled out the card and put it back. So this is something that is important, because you need to be able to set it up in the space that you have, and you need to be able to move it. And that's something quite useful as well. Yes? What do you, I'm sorry, but what do you refer to as RCS? Ah, okay. Okay. Yeah, basically, so the question was about the software. And to be honest, we have a very good relationship with KUKA, because KUKA don't really see themselves as a software company. So that makes a big change. So they have some products that they sell, but even they are usually licensed from other companies. So that makes it for us a very good basis for collaboration, because basically whatever we do, we in extension sell KUKA robots. So, but beyond that, we are a KUKA system partner, but we don't earn a commission from them or something like that. But we have a very good collaboration. So if we need robots for a project, we can usually very easily ask them. And robotics and probably all kind of machines and probably also software is also a very local matter. So in our case, with KUKA, it's very convenient that they are headquartered in Germany. So this is actually like 1.5 hours from where I'm living. So whenever we need any kind of support, we can just drive over there or call them and have a very short connection to them. So this... it's running, basically, the software itself is running in the Azure cloud in Microsoft. We use Forge for the 3D visualization. And our software basically can run in any place where you can run .NET code. So right now we have it implemented for Autodesk Dynamo and for McNeil Grasshopper. These are like core systems, but we could basically implement it in all different kinds of software environments as well. Mm-hmm. Yeah. Thank you. Yes, please.
So the software looks like it's getting a lot of user-friendly. There seems to be a community out there that's building, bundling a lot of the tough code and Dynamo and such. Is the hardware getting easier? Is it getting easier to add components and modify the robot itself?
Yeah, so we are asking about the hardware. Hardware, it really depends, but hardware wasn't ever really that complicated because you need to imagine that robots were really made to be used on the shop floor by people who don't have a degree in computer science or whatever. So they were expected to be able to just work with the robot. So this is why the robot itself was always relatively easy to control. Of course, relatively being sometimes they're not user interface experts, but if you kind of think a little bit, you can get into that as well. About the controlling external devices, I mean, a big change for us is, of course, 3D printing, more for smaller robots, of course, that we can very quickly develop tools for that. But the interfacing is not particularly complicated. So if you want to send signals to some kind of external extruder, you use this kind of back-off system, for example, and they're also used, for example, in home automation. So these are things where you can, if you're lucky, you can go to your local electrician and he actually knows how to set these kind of things up. So these are not highly proprietary robot stuff, but this is more general automation technology that you can find in many places. So that makes it definitely easier to do that. And of course, there have been developments, just a newer generation of controllers, they have touch screens. So that sounds a bit petty, but it's still kind of important just to be able to have a smaller controller, move around with it, so you're just able to react quicker than you have these very old industrial interfaces that are nearly too heavy to hold. Okay. So thank you very much. You just drop by if you've got any questions or contact me through the app or by email, so I'm happy to answer any further questions you might have in the future. Thank you.